Hello, and welcome to the final section in the chapter on integration, and what we're doing today is numerical integration. Okay, integrating things numerically to get an approximate value. Okay, so we'll start with something we know all about, and it's fairly straightforward. We want to find the area under some curve, in this case x squared, from x equals 0 to 3. Okay, so we write it in this form. It's a definite integral of the function x squared from 0 to 3. We can find the antiderivative, which in this case is x cubed over 3, and it's simply 9, the upper bound, minus 0, the lower bound, so it's 9. Okay, so that's the area under that curve. Okay, but let's make a slightly more complicated version. What if our function now is e to the x squared, and we're just going from x equals 0 to 1? Well, we could write it in this form, and that would be correct. However, what do we do from here? What is the antiderivative of e to the x squared? Well, in fact, we don't know, and we can actually go further with that statement. It's not simply that we don't know because we haven't learned that yet. There is no elementary function that we can write as the antiderivative of this. Okay, it simply doesn't exist. Therefore, we can't just do as we did above by finding the antiderivative, plugging in the values. We have to approach this in a different way, and as the title of this suggests, we're going to do this numerically. We're going to find an estimate numerically for the area under that curve. Okay, so just to remind ourselves what this looks like, so this is e to the x squared between 0 and 1, and that's the area under that curve. And so as we start doing these numerical integrations, we actually use things we've seen before, and we'll start with the left-hand rule. So remember, this was where the rectangles had the height of the function at the left-hand end. That's where it gets its name. And we found the area of each of those rectangles, sum, and that's our estimate using the left-hand rule. Just a quick reminder, the delta x, the width of each of these, well, it goes from 0 to 1, and we're going to stick with 4 rectangles throughout. So the delta x in this case is 0.25. Okay, so our integral from 0 to 1 can be approximated by, of course this is an approximation, so it's f of 0, the height here, times by the width, the 0.25, then f of 0.25, f of 0.5 and f of 0.75, and so they're all multiplied by that delta x. So when we're actually calculating this, we can factor out that delta x because it's the same in each case. And then we just plug in the values to the function, the f of x, like so, and this comes to 1.28. Okay, and it's clear that that's an underestimate. We can see that from the graph, and we'll talk a little bit about under and over estimates later. Okay, we can go on to the right-hand rule. This, of course, is very similar, except we take the height of the function at the right-hand end of each rectangle here, 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 and here. The delta x is still the same. And so now, of course, we get f of 0.25, 0.5, 0.75, and 1. Still multiplied by that 0.25, so we factor that out. And again, if we just plug in and find the value there, well, it's 1.71. And in this case, again, it's clear that this is an overestimate. That's very easy to see from the graph. Okay, we will look at a couple more rules. There's the midpoint rule as well. Again, we've seen that before when we were doing our Riemann sums. And again, this was the height taken at the midpoint of each rectangle. So here, 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 and here. And again, the width is the same, and well, just plugging in. And this time we get 1.45. Okay, and just even looking at this, it's clear that this is a better estimate, right? We're missing some bits and we've got some bits extra, but this seems like a reasonable estimate. And again, we'll talk about errors in a moment. The next thing we're going to look at is a little new. This is going to be called the trapezoid rule. And just to remind ourselves about a trapezoid, so this is our trapezoid, the area of a trapezoid. So we take the average of the two heights, in this case a and b, so it's a plus b over 2, then multiply by the width, in this case it's h, and that gives the area of that trapezoid. Okay, and we'll need to remember that as we're going through here. So here is our trapezoid. If we just zoom in a little bit over here, just to make it clear what's going on, you can see we have the straight line going up here, and the curve of the function here. Okay, and that's a trapezoid formed around, and in this case slightly above the function. Okay, so as we zoom back out, let's think about how we do this. Well, we squish the picture down a little bit. In this case, the first trapezoid still has a width 0.25. That's our h. Maybe we'll bring that diagram in here. And now the two heights are f of 0 and f of 0.25 over 2 for this particular trapezoid. And then we move on to the next one. Similarly, we get 0.25 and 0.5, and the next one and the next one. Okay, but now let's think about calculating this. Well, again, we've got the 0.25 everywhere, so we can factor that out. We also divide by 2 in each case, so we can factor that out. And when we think about what's left, we get the f of 0 and the f of 1. But we have to get 2 of the f of 0.25s, okay, in the first two terms here. We get 2 of the f of 0.5s, and we get 2 of the f of 0.75s. Okay, and no matter how many rectangles we do, except for the first one and the last one, we're always going to get 2 of them. Okay, so this leads us to this. Okay, so I say we factor out the 0.25 and they're divided by 2. We just get the f of 0, then we get 2 of each of the middle ones, and then the f of 1 at the end. And once we figured that out, well, again, we just plug the values in and race straight to the answer, which in this case is 1.49. Again, it appears this is a slight overestimate. Remember, our trapezoid was slightly above the curve here. Okay, and this finally leads us to the Simpson's rule. Okay, and so Simpson's rule looks something like this. We won't go too much into the derivation of the formula here, but just give a brief explanation of what this does. Okay, so Simpson's rule, rather than taking kind of 2 points on the curve, is actually going to take 3. Okay, so if we take our curve, our function here, represented by the blue line, and we take 3 points on it, what Simpson's rule does is approximates the curve with a quadratic through those 3 points. Okay, so if we take any 3 points, we can approximate that with a quadratic. And in this case, that's the red dotty line. And Simpson's rule does that to find an estimate for the area under the curve. Okay, now as I say, I'm not going to go too much into the why it comes out like this, but this is our formula for Simpson's rule. So in this case, we take the delta x, which is still the same as it's been previously, over 3 this time. And then we get this kind of pattern 1, 4, 2, 4, 2, 4, 2, 4, 1. So the first term, the f of x1, 4 times the f of x2, 2 times f of x3, and so on. The penultimate term, the next to the last one, is 4, f of xn, and then the very last term is just one of those. Just a quick note about this, it does mean we have to have an even number of n's. Okay, so to get the 3 points together and to get the sort of the right number to form this pattern, we do need an even number n, okay, an even number of breakups of these. Okay, so applying that to the integral we've been doing, so we get the integral from 0 to 1 of e to the x squared. In this case, it's approximated by, so again, we have the delta x over 3 outside now, from here, and then we just get the 1, 4, 2, 4, 1. And of course, once we've written in this form, it's fairly straightforward to just plug the values in and get that. Okay, so if we summarize our numerical integration, we have, in this case, the 4 rules here. So we're going to assume that f is a continuous function. That is important. We gloss over that a little bit, but it is important that f is continuous for this to work. And again, we set the delta x to be the b minus a over n. And we've got our x1 term is a, x2 is a plus delta x, and we keep going along, adding the delta x's all the way up to xn plus 1, which is b, the last term. And our left-hand rule is given by this, which we have seen before. So it's to take the delta x outside, and just f of x1, x2, all the way up to xn. The right-hand rule is very similar, except we start at x2 and finish at xn plus 1. The trapezoid rule here, so now we take the delta x over 2 outside, and we have the first term plus 2 times second term, 2 times the third term, and so on, 2 times the xn, and then just 1 times f of xn plus 1. And then finally, Simpson's rule we just saw, we have delta x over 3 outside now, and then we have this 1, 4, 2, 4, 2, 4, 1. Okay, so those are our various rules. Let's just give a quick summary of our estimates. Okay, so these are the 5 estimates we found, and then we do have the actual value at the bottom there. And you can see the left-hand rule was an underestimate and fairly far away. The right-hand rule was, again, not that close. The midpoint trapezoid and Simpson's rule were all much better estimates, and it appears that Simpson's rule gave us the best estimate here. Okay, so speaking about estimates and how wrong we can be, we'll talk a little bit about errors. And first, we'll just think about the graphs. So as we said when we were doing this, left-hand rule was clearly an underestimate. In fact, that was because the function's increasing. Okay, as long as the function's increasing, it's clear that the left-hand end will be below the curve. So this will be an underestimate, and a similar sort of logic applies for the right-hand rule. Because it's increasing, it's an overestimate. The trapezoid rule was also an overestimate, again, because of its increasing nature. Okay, we can see that the trapezoid is a little bit above the curve. Whereas the midpoint, this one was a little harder to see. Okay, maybe if we just zoom in here, this is a slight underestimate. Okay, and the reason for that is not just because it's increasing, but it's increasing and concave up. What that means is the bit that's above that we're kind of missing here is just slightly more than the bit we had kind of extra here. Okay, so because we're increasing and concave up, the midpoint rule is actually going to give us a slight underestimate. Final theorem, which is the error bounds for the trapezoid and Simpson's rule. And these are a little involved, so we'll talk about them. Let's look at the first one. So ET, this is what we're going to denote as the error bound for the trapezoid rule. That's why the subscript of T there. Okay, and we're going to assume that if f has some sort of continuous second derivative, and that m is an upper bound on the absolute value of that second derivative between a and b. Okay, that's important. The m is probably the most complicated bit here. Then our ET is less than or equal to b minus a cubed divided by 12n squared multiplied by m. Okay, so remember b minus a, well, that's fairly straightforward, that's the bounds. We cube that, divide by 12n squared and multiply by this upper bound on the second derivative over the region. A couple of notes on this. Obviously, as the b and the a get further apart, this gets larger. Okay, because the numerator here gets bigger. And that should make sense. As our region gets bigger, we should expect a bigger error. But as our n gets larger, our errors get smaller. And again, that should make sense. The more rectangles, or in this case trapezoids, we take, the better the estimate is. And I say we'll talk about the m when we do an example in a moment. And the error term ES for Simpson's rule is fairly similar. Now we take the fourth derivative to find m. Again, m is the upper bound and the absolute value of the fourth derivative over the region. And then our error term is given by, well, ES is less than or equal to b minus a to the power 5. And this time we divide by 180 n to the 4 and multiply by m. So again, it does look fairly similar. Okay, and I say we'll just apply this to find the error for the trapezoid rule on the example we've been looking at. So what we've been looking at is e to the x squared with 4 trapezoids, 4 regions. Okay, well, our a is 0, our b is 1, our n is 4, because we have these 4 trapezoids. Well, what is our m, though? Okay, m isn't straightforward. We have to actually do some calculations to find that. Well, we find our function, and we find its derivative, and therefore its second derivative. Okay, so there's a little bit of chain rule, and I guess also some product rule in there to find the second derivative of this. And then we're looking for what is the biggest that this can be in the region 0 to 1. Okay, well, it turns out that that's at x equals 1, right? This is an increasing function, so the largest this will be in the region 0 to 1 is at 1. So we plug in x equals 1 into this function, we get 2 plus 4 and then e to the 1, which is of course just 6e. So we're going to take that to be our m. Okay, the largest that the second derivative can be in the region. And just a quick note on that, it's tempting to always put in just the largest value of x here. It's not always the case. Okay, you have to look at the function, the second derivative, a little bit carefully to decide where it's going to be largest. It's often at the endpoints, but even then it's not necessarily true. Okay, well, having found that, however, this is fairly straightforward. Okay, if we look at the rule, it's b minus a cubed over 12n squared multiplied by m. So we just plug in all our values and we get 6e over 192, which is approximately 0.08. Okay, and remember our actual error was about 0.03, so we did slightly better than we might expect. And remember, this is an upper bound for the error. Okay, the e of t is an upper bound for the error that we get. And sure enough, that's proven to be the case in this case. Okay, so I'd say defining the m is probably the most complicated bit here. Everything other than that is fairly straightforward, just plugging in values. And that's about it for numerical integration.